Okay, so moving on. So as I promised, we're going to look at how to standardize any normal distribution into the standardized normal distribution, so we can then go ahead and use the tables to answer probability questions based around that distribution. So firstly, let's look at two different distributions. So we'll take x follows a normal distribution of 32 with a standard deviation of 4. So the mean is 32 and the standard deviation is 4. And I want to try and find the probability that x is greater than 37. Okay, there are no tables designed for this particular distribution. There's only tables designed for everybody's favorite, the Z distribution. It follows a normal where the mean is 0 and the standard deviation is 1. So what we're actually going to try and do is we're trying to turn this X distribution into the Z distribution. Okay, so let's just quickly look at what each of these will look like if we were to sketch them. So this distribution, the mean is 32. The standard deviation is 4. So I'm actually expecting 36 to be around about here, 40 to be here, 28 and 24. Don't worry too much about getting those values exactly one standard deviation away. We're not really interrogating the accuracy of the diagram. Okay, but to emphasize that probability statement is really this area here. I'm looking for this area, I'm looking for this probability in my problem. All right, so once again, there are no tables for this distribution, so there's nothing to help me do this. What I'm going to think of instead is the standardization formula, which I'll talk about in more depth in another video, so you can check out that video. But for now, we're just going to use it in its raw form. So Z equals the X value minus the mean of the distribution, all divided by the standard deviation. For this question, the Z value is 37 over here. So we're going to go ahead, say the probability we're transforming into the Z distribution, the standardized distribution, is greater. Going to use this formula to transform 37 into a Z score. So that's going to be 37 minus 32 all over the standard deviation of 4. That works out to be Z is greater than 1.25, 5 over 4, yep, greater than 1.25. What does this look like on the diagram? Well, for this distribution, the mean is 0, I have 1 standard deviation, 2 standard deviation, -1, -2 standard deviations, and I was looking for it to be 1.25. These areas are going to match each other perfectly. They match each other exactly, which is why standardizing is so useful. Now that we've standardized, I can find this blue area and it will match the answer to the black area. If I work out this probability here, I've worked out the probability in the original question. All right, so let's go ahead and do that. This is not table ready. Why is it not table ready? We're looking for greater than, and the tables are built for less than. So 1 minus the probability that Z is less than 1.25. All right, and now we are just ready to look that up in the tables. 1 minus 0.8944, which leads to a final answer of 0.1056. Okay, so this is how we're going to standardize from the normal distribution, any normal distribution, into one that we particularly want to work with. Okay, so this is how we're going to standardize any normal distribution, and then we can make use of the tables and work out from there. Okay, so let's add some context to that now. We'll go for this question. The measure of intelligence, IQ, of a group of students is assumed to be normally distributed with a mean of 100 and a standard deviation 15. All right, so the very first thing to do, let's just find the distribution. Normal distribution, the mean is 100, standard deviation 15. Don't forget to write it in the correct form with the squared. That's what we're looking for. Find the probability that a student selected at random has an IQ less than 91. So let's write that probability statement. So the probability that the student's IQ, the X is the random variable of the value of the student's IQ, X is less than 91. Okay, a couple of things just to check before we even go. 91 is smaller than the mean, and I'm finding less than 91, so I'm expecting this probability to be less than 0.5. Definitely. That's going to be my first sense check as I go through this question. Okay, next we're going to go on to standardize. So that equals the probability that Z is less than the standardized score. 91 minus 100 all over 15. It's the probability that Z is less than -9 over 15, so negative 0.6. Okay, trying to find the probability that Z is less than negative 0.6. Okay, let's take a quick diagram. Negative 0.6 is on this side. I want to know the probability is less than that. This is not table ready. I know that I'm going to need to reflect this. Positive 0.6. All right, so this is the same as probability Z is greater than negative 0.6. All right, still not table ready. I know I'm going to do a 1 minus on this. 1 minus the probability that Z is less than 0.6. So we're talking about this red area over here. 1 minus that area should give me my answer. And I can find that red area in my tables. All right, and the probability I'm looking for, 0.2743. Have a think, does it make sense? Yes, it's smaller than 50% like I anticipated to begin with. That's the value that I'm looking for. Okay, and taking that on. The probability that a random selected student has an IQ of at least 100 plus K is 0.2090. Find to the nearest integer the value of K. Okay, so we're still going to be thinking about standardizing, and we're going to be using our tables. The clues for me are this 4-digit probability. I know that that's in the tables, so that is going to be linked to a particular Z-score. And since I know the distribution that we're working in, I can standardize my Z-score to get here. Okay, so let's start. And this time I'm actually going to start with the diagram. Let me see exactly what's going on. So the probability that a randomly selected student has an IQ of at least a particular value, at least means more than 100 plus K. It's going to be somewhere over here, because I know the area above it is going to be 0.2090, which instantly lets me know that the area below it, so 1 minus, is going to give me 0.7910. Okay, so this is the real world contextual situation. The mean here was 100. Let's not forget the distribution itself. X followed a normal distribution, 100, and a standard deviation of 15. Okay, this should be able to translate to the standardized distribution. Okay, and I'm interested in what Z-score sits right here. What Z-score is going to match up with the 100 plus K? I know the 0 matches up with 100. What will match up with 100 plus K? So looking at the tables, the Z-score that has 0.7910 below it is 0.81. Okay, so standardizing is going to link 100 plus K and 0.81. So let's go to that standardization formula. So it's going to link the real world value of 100 plus K with the Z-score 0.81. So let's put in the Z-score. I'm going to leave X as, no, I can put X in as 100 plus K minus the mean of 100 all over 15. And then I just need to rearrange to solve from here. All right, so some quick rearranging. The hundreds cancel out, multiplied by the 15. Then we get 12.15. All right, so that's the value of K. Being careful, in the question we were told to find it to the nearest integer. K is approximately 12. Okay, so making use of standardization here, making use of the diagrams, and making use of the tables for a nice problem-solving normal distribution question. Okay, and let's go for one more. So the random variable X has a normal distribution with a mean of 20 and a standard deviation of 4. Find the probability that X is greater than 25. Okay, so let's find the distribution. So let's start by writing down that distribution. X follows a normal distribution where the mean is 20 and the standard deviation is 4. And we want to find the probability that X is greater than 25. Okay, so let's standardize straight away. So I'm going to get the probability that Z is greater than 25 minus 20 over 4, greater than 1.25. And I'm getting some deja vu here. So 1.25 being one of our popular Z scores. So obviously 0's in the middle. I'm trying to go greater than 1.25. Tables are not set up for that. I need to do a 1 minus. So I will be subtracting this red area, which I can find in the tables, 8944. Final answer, 0.1056. And that's what we're looking for. All right, moving on to part B. So we're asked to find the value of D such that the probability that it's in between 20 and D is 0.4641. Okay, just because it's gone off screen, let me come back with that distribution. So it was 20 and a standard deviation of 4. Let me put this onto a diagram then. Okay, so where are these values going to go? So these are Okay, so these are the real world values. So the mean is going to be 20. D is going to be to the right hand side since it's larger than 20. And we're looking for the area in between them. Apparently that is 0.4641. Okay, what I notice instantly here is since I've used the mean, I do know how much is to the left hand side of the mean. I know to the left hand side I have 50%. So actually, if I drew this diagram and I was concerned about everything to the left of D, that's going to be 0.9641. And that's actually a better situation for me to go ahead and find out the value of D. This can be looked up in the tables. That will instantly give me the Z-score for D, and the Z-score will match the real world value, and that's what I'm going to use to respond to this question. Okay, so what Z-score has 0.9641 below it? That's a Z-score of 1.8. That's going to match the real world value of D, and we're going to match them through the standardization formula. Z equals X minus mu, all over the standard deviation. Z-score is 1.8, this is an unknown value D, minus 20 all over 4. So I'm going to end up with 4 times 1.8, multiplying across by the 4. Let's add on the 20, and that's going to give me my value of D. And my final answer, D equals 27.2. All right, so just looking at that in comparison to the distribution, let's see if it makes sense. It definitely needed to be bigger than 20. There's quite a large percentage there, so I'm expecting it to be at least a couple of standard deviations away. And yeah, this is approximately 1.5 standard deviations away from 20. All makes sense to me, confident that that's correct. So once again, we've used the contextual, the real world values, we've used the standardized values, we've used the Z-scores, the tables, and the standardized formula, all in this one question.